problems before we move on to chapter 9. Let's do number 5 here. The moment of inertia for this system. It's on page, I don't know what page it's on. It's exam 4 though. Number 5. Exam 4, number 5. Not at all. Today I have to let cover because we have an interview an organic chemist, a nice organic chemist.
Top priority. One, I like to have fun.
A fun and nice organic chemist.
When my recent game, your wife sometimes reads.
My wife?
Yeah. One.
All right, everybody, number 5. Number 5. Come on. That's being nice. Good example of what you'll see on the test, this one, okay? Let's stop in about 20 seconds. If you finish this one, you can go on to do number 1. Number 1, if you finish this one. I'll stop at 2:30, 2:30, 2:30. 5 more seconds. C. Right answer. I'm pretty sure. Because look, there are 2 parts to this system. You have the bar that's rotating about a central axis, and then you have a particle at the end. So the moment of inertia for a bar, if I remember correctly, it's 1/12 mv squared. Is that right? Yeah, so that's what a lot of you did. You said 1/12 of the mass, which is 3, times the length, which is 4, squared. That's 1/12 of 48, which is 12 kilogram meter squared. Kilogram meter squared. All right, but that's not all. Like those of you that put D, that's where you stop. There's also this extra piece out here. It has a particle at the end of it. And the moment of inertia for this is equal to mr squared. Right? Remember sum mr squared? But in this case, there's just one particle, so there's no summation. And that's going to be 2 kilograms times 2 meters squared. That's 2 times 4 is 8. That's not right. No, I'm sorry, not 2 meters. It's yeah, it is 2. 2 times 4 is 8. What was my problem? Do I not have the right answer? Hold on, let me. The mass is 3, it's 4, 16. Yeah, it should be 20. I'm sorry. Let me go back and mark. Do I have a problem here?
4 squared is 16 divided by 4 is 4.
Oh, yes. Right here. Right? That's what you're saying? All right. 4 kilogram meters squared. And then 4 plus 8 is 12. Well, that is what a lot of y'all put, right? Yes. Okay, let's do number 1. Y'all clear on that? There are 2 parts you have to add up. The moment of inertia. All right, number 1. After this one, we'll do number 4. So go on to number 4 if you finish number 1. All right, let's try to do about 20 more seconds. Stopping in 10 seconds at 225. 225. It's 5 more seconds. Let's guess if you don't know. Okay, so here we have a wheel. It's rotating such that it has a linear velocity equal to 2 meters per second. That means that the velocity down here is 2 meters per second. And I want to know what is the rotational kinetic energy. So the kinetic energy, rotational, is 1/2 I omega squared. So I need to know omega and I need to know I. Now I for a disk, oh no, this is a sphere. Oh gosh, what is it for a sphere? Did y'all look that up? 2/5 mr squared. So that's going to be 2/5 of the mass, which is 10 times 2 squared. Uh, 4 times 4, 16. I got 16, is that right? All right, so it's going to be 1/2 of 16 kilogram meters squared times omega. And then for omega, we need to say, well, V is equal to omega times R. So omega is V divided by R. That's going to be 2 divided by 2. 2 meters per second divided by 2 meters. So it's going to be 1 squared. So that's equal to 8. So C is right. That's very good. I always feel like this is kind of vulgar, forgive me. But I always feel like this is somebody, the bird, y'all know what the bird is? Like the middle finger. That's always what that reminds me of. When y'all get a C like that. Because it's like the 2 knuckles on either side. Sorry, was I recording that? Ah, shoot. Well, let's do number 4. Good approach on questions, ranking questions like this, is you look for the biggest and then you look for the smallest. And then you don't need to worry about what's in between. If you can pick out the 2 extremes on either end, often you can select the answer. What's the biggest moment of inertia and what's the smallest? All right, let's stop at 125. 125. All right, folks, B is right. So which of these has the bigger moment of inertia? The bigger moment of inertia is going to be A, because when I'm rotating about this axis A, I got all this mass out here at a big radius. It's rotating around a big radius, all that mass. So A is the biggest. So I know I can get rid of D. And now I want to look for the smallest moment of inertia. That is the one that has the least mass at big radii. So which one is that going to be? Well, this one has a bunch of mass out at sort of half the length. It's either going to be C or D. If I have an axis along a bar, then that bar doesn't contribute anything to the moment of inertia because R is equal to 0 for that. And so which is it going to be? Is it going to be C or D is the smallest? Well, they're very similar, but if I bisect D here, then I have this bar which goes out this length. But if I go along this one, then I have this bar that goes out twice that length. So this one, when it's rotating about C, has more mass out at bigger radii than does if it's rotating at D. I have the same amount of mass, but it's at smaller radii. So D then is smaller than the moment of inertia at C. So I can get rid of this one, and then I can also get rid of this one because C is not equal to B. So B is the right answer. So we put, yeah. All right, let's see what else we got here. Let's try number 6. This one's a little bit different than some of the ones that we've done before, but it's a good example for the exam. What you want to think here is that the initial momentum, Li, is equal to Lf. And think about what are the two things in our system. I have a couple of different things that are coming together in this system. Okay, doing pretty well. Now ask your neighbor, see what they put. All right, I'll stop in about 10 seconds. I'll stop at 143. 143. All right, E is right. Good. Good job. Let me show you. So this one's a little bit different than the other momentum problems that we've done before. What I have here is I have a bar that has this moment of inertia, and it's rotating at this speed. I'm going to sort of think about this in terms of an axis. So here's my axis, and here's my bar, and it's rotating around at 3 revolutions per second, and it has a moment of inertia of 4 kilogram meters squared. And so it has an angular momentum of 4 times 3, I times omega. That's equal to 12. And then this flywheel, they bring this flywheel up next to the bar and it engages on the same rotation axis, on the same axle. And so here's this flywheel. It's not moving at all at first, so it has no momentum. But then they connect together And now I want to know what is omega final for that fly rod, or what is omega final actually for both of them, because they come together, they engage, and they start spinning at the same rotation rate. So I know that Li is equal to Lf. That is 12 kilogram, I'll just write 12, is equal to the final moment of inertia times omega f. And the final moment of inertia is going to be 4 plus 8, because my flywheel has a moment of inertia of 8 kilogram meters squared. 4 here, 8 here. I just add them together, because moments of inertia, they add up like mass times omega. And so omega is equal to 12 divided by 4 plus 8, which is 12, and that's equal to 1. 1 revolution per second. Notice I didn't have to convert my velocity to radians here. The units carry over. That's a good example of a momentum question, like you'll see on the test in a couple of weeks. Okie dokie? How y'all feeling about this chapter? It's kind of a big chapter. There's a lot in it, so don't put off reviewing it. I would go tonight and review it and print out some of the old exams and work through those questions, just a few a day. It'll help you to get prepared for the next exam. Okay? All right. Let's start on the next chapter. Some of it you've probably seen before, either in chemistry or high school physical science. I do want to remind you about the food drive. It concludes on Monday, but you'll have all day Monday to bring stuff. We're doing pretty well right now, but we're really hoping everybody to bring 5 or so items to the food drive, okay? And then I'll give the whole class 10 points for that. Let's see. So we're on solids and fluids. First of all, you just need to know the different states of matter. I think y'all know this. This is like 3rd grade almost. So the states of matter are solids, liquids, and gas. Just know the basic definitions for them. In solids, they have a rigid structure. The atoms don't move with respect to one another. Liquids, they have a more fluid structure. That is to say that in a solid, the atoms are always a certain distance apart from one another, just like how we described a rigid body in chapter 7 or whatever. But in a fluid, those particles can sort of move with respect to one another, move around one another. And in a gas, the particles don't touch. In an ideal gas, anyway. Collectively, we'll call these two fluids. So when we talk about fluids, we'll be talking about liquids and gases. There's also a 4th type of matter, plasma. You ever been to Spencer's? They still have those stores, those really vulgar stores, where you buy like the dog poop in a box. You know what I'm talking about? They have good coffee cups. We got one. Y'all care to hear a story? When I was a kid, I have a very good memory of this, buying a coffee cup for my dad for Christmas, but it had like a roach in it, right? You know what I'm talking about? Like a ceramic roach stuck to the side, so you're drinking your coffee and there's a roach in it. And like you threw it up in the air and got it for Christmas. Alright, so anyway, at Spencer's they have those balls with all the stuff going out to the edge, and you stick your finger on it and bzzz, the blue flame or whatever. That's a plasma. A plasma is just an ionized gas. It has a plasma inside of it. It's an ionized gas with approximately equal numbers of positive and negative particles. Plasmas are often very hot. Because when you heat a gas to a very high temperature, it ionizes the gas. It separates the electrons and the protons, and that's what a plasma is. But obviously, with that device that you have at Spencer's, where you get these little blue arcs, that's not like the surface of the sun, right? It's ionized in a different way. But a plasma is always going to be an ionized gas. So gases can be ionized in other ways too. Let's see. Do I have this clip? We're not going to watch the Prestige one. I'm going to show you this one. This is a grape in the microwave. You ever done this? Stuck a grape in a microwave? It's pretty cool. Or maybe go to a friend's house. I don't think it'll damage your microwave. I'm pretty sure that it won't. But you can try it out nonetheless. It's pretty cool. Tell your friends that it's plasma. All right. So there's another type of matter. It's not really a type of matter. I'm just going to list it here, though, as a type of matter, which is called dark matter. But it's not really a phase of matter or a state of matter. Instead, dark matter is matter that doesn't emit or reflect light. Astronomers discovered it, I don't know, back in the 60s, 70s, a little bit earlier. And because it didn't emit or reflect light, then they called it what? They called it dark. Dark matter, that's why it's called dark, because it's not bright. It's dark matter. Like I said, it's not really a state of matter, but it makes up most of the universe, so it's kind of cool to think about. And we don't really know what it is. Let's see, this was first inferred through the observations of rotation curves of galaxies. And they did something kind of cool. You take a galaxy, kind of like our own. We live in a spiral galaxy, and we sort of live in between the arms of the spiral galaxy. But if you look at a galaxy that's far away, then you can do two things. You can determine what is the mass of that galaxy by looking at the number of stars, by looking at how bright it is, and we'll call that the light mass. So this is determined from the number of stars, how bright the galaxy is. And then we can also look at the speeds of the stars, because you got these little stars sitting in here, billions of stars, and you can calculate or measure what is the speed of the stars. And depending how fast those stars are going will tell you something about the mass of the galaxy. And so that's called the dynamical mass. And that's from the speed of stars. And so they looked at these galaxies comparing the dynamical mass and the light mass, and which one do you think they found to be more? The dynamical mass or the light mass? Well, their conclusion is that these galaxies are going to be made up mostly of dark matter. So which one of these would be bigger? The dynamical mass would be bigger. In fact, they found that it was a lot bigger, that the dynamical mass is much bigger than the light mass. And so they say, well, the difference, the material that's in these galaxies that we can't see, we don't know what it is, but we'll call it dark matter. And it's thought that about 90% of the universe is made up of dark matter. So most of the universe is made up of this material that we can't see. Not really sure what that is. If y'all figure it out, a Nobel Prize for you, maybe. For a long time, they thought that it was dust or rocks out in space, but there's not really enough dust or rocks out in space to make up this dark matter, even though those things are dark. Some people thought that it was molecular hydrogen, because molecular hydrogen, when you have two hydrogen atoms, they don't emit light very well. It's pretty dark. It's not entirely dark, but it's pretty dark. but there's just not enough molecular hydrogen to account for 90% of the universe. Probably it's some sort of exotic material that we just don't know, we just don't understand right now. So we don't really know what dark matter is, but we know that it exists because we observe its properties. Just know that dark matter is this material that makes up most of the universe, and it's based on this difference between the dynamical and the light mass. Let's see, elastic properties of solids. You'll have some problems in the workbook problems dealing with this, and you do need to know what stress and strain are. Stress is the force per unit area that acts on a solid. And then strain is a measure of deformation. Of a solid. So stress causes strain. When you stress an object, it causes strain in that object. And I'll show you what that means, like in a linear scheme. Stress and strain are also proportional. They're directly proportional, in fact. At least for most materials, for most stresses. So stress, then, is directly proportional to strain. The more I stress an object, the more I'll strain it, the more it will be deformed. And these two are proportional by the elastic modulus. So I can develop this equation, and engineers use this a lot, where stress is the elastic modulus. I'm going to call it EM here, though we'll give it a particular variable here in just a minute. The elastic modulus times the strain. Bless you. It's just a, what's that called, a proportionality constant. It's different for different materials, like we saw for springs, like we've seen for various things, like for the coefficient of kinetic friction, that this is for a particular material. You apply a stress to a material, you measure its strain, and then you calculate its elastic modulus. And engineers, they have big books with tables for all these different types of materials. You can pull those elastic moduli for those different materials. You only really need to be concerned about one-dimensional elasticity, tensile stress and strain, and that is if I have an object that's a certain length, L0, and then I pull on it by applying a force to it, I pull it, I stretch it out. Stretching out, is that the stress or the strain? Like this difference in delta L. Is that my stress or my strain? When I talk about how much longer the object got, that's my strain, right? When I talk about the force, or actually it's going to be the force per unit area, that's going to be my what? My stress. Right, so when I talk about the change in length, that's going to be my strain, and the force is going to be the stress. All right, so the stress is equal to Young's modulus. Engineer some years ago, times the strain. Here F is the force, L0 is the original length, and A is the material's cross-sectional area. Let me write down that, cross-sectional area. And delta L is the change in length of the material. All right, it's the strain. All right, so our stress is a force per unit area. It's going to be F over A. That's my force per unit area. It's going to equal to Y. That's my Young's modulus, my elasticity modulus, or elastic modulus, times the strain. And the strain here is going to be delta L over L0. If you're looking at these in 2D, they look a lot similar, or even if you look at them in 3 dimensions, they look a lot similar. But here we're going to use it in 1D. Okay? In 2D, this would be like a change in area over the original area. In 3D, this would be the change in volume over the original volume. They look a lot the same. Let's do an example. We'll wrap up soon. This is a list of Young's moduli for different materials. You'll be given this. In fact, this is on your equation sheet. So just be aware that these quantities are there. I won't give them to you in the problem likely. You'll have to know to look on the table. Let's try this problem. I have a tendon. I apply a force to it. I want to know how much does it stretch.